Okay, welcome back. So we were discussing a generalized framework for making a small signal model out of a generic nonlinear element when put in a network, right? And then there were some confusion about how to proceed uh, with the theory that I was trying to inculcate. So we'll do that. We'll do that today. But before going there, just a couple of notational things that needed to be cleared off. So we'll be using these notations throughout the course. So for example, what till now what we have been doing is saying that, let's say we have a current under DC condition. I'll just sketch a network and then try to make the point. So what were we saying? We were saying that if we have, let's say, an input, let's say V, input voltage VA, and this is R, this is some nonlinear element, and let's say the current through this is I, let's say IA, right? So let's say, okay, let's say this is V in, and the current through this guy is IA, and the voltage is VA, and then we change this input voltage from V in to V in plus delta V in. So naturally, there will be some increments. There will be some increments in IA and VA. So increment in IA, we were denoting it as delta I, delta IA maybe. In this case, increment in VA, we are denoting as delta VA. So since this you see that it's all a play of delta. So what people tend to say that too much of notation. So what we'll do, we'll get rid of this delta and we will use a different notation. And the notation that we'll be using also in this course is the following. So when we say capital I and capital A, that is the subscript is also capital, this will refer to operating conditions or operating point or quiescent points. Okay. But then what is this delta? How will you denote delta? So whenever we say delta I, so delta I A will be referred to as small I subscript small a. Okay. So this we will refer to as incremental currents or voltages, right? Okay. And there is another notation that is, so if we have to denote the total, right? So this is incremental. So if you have to denote the total current and voltages, so in this case, it's IA plus delta IA. So this is denoted as small I caps A. Okay, so this refers to total current, in this case, total current, right? I should write it as, if it's a voltage, it should be VA, V caps A. This is total voltage. So basically, all this is to simplify the notations and get rid of the delta. Okay, so this is something that we'll be using throughout the course. But natural question that will come to mind is, not often we use A, B, C as subscripts. We have 1, 2, 3, right? I1, I2, I3. In that case, what we'll still stick to is, in that, let's say if I denote the current is I1, right? So we'll stick to the case and say that incremental is still I1, right? Operating point is capital I capital I subscript 1, incremental is small I subscript 1, even though there is no shorthand for 1. And if we have to then mention what is the total voltage, we will write it out as total. Total voltage is capital I1 plus the small I1. Okay. So that's the only point of confusion, but you should be, once you start doing assignments, you will get used to it. Another point of confusion that sometimes arises is when there is a crossover of wires. So there are two ways of representing a crossover. So let me show both of you, and then I'll also emphasize which one we'll be using in this course. So for example, let's say I have a 2 points A, B, C, D. And there is a one piece of wire connecting between A and B, and another piece of wire connecting C and D while not touching the existing wire. So normally there is one notation which goes like this. I'm sure you're familiar with this. Now there is another way of representing the same, is to say that, okay, so this is no crossover, right? So this is no connection between crossing wires. And if we, in using the same notation, if we have to show what is meant by, if I have to denote these wires are actually touching each other, then I simply get rid of that semicircle and connect it like this. This should mean these are crossing, right? So here we have crossing with intersection, or rather simply say intersecting wires. But there is another way of representing the same things. That is, so let me use a different marker. So, but according to this method of showing crossovers, so this is one way also of showing that there is no crossover, but you have to be consistent with the methodology and then say that if I have to denote a crossover, I'll have to denote it using a dot. Right? So this means there is an intersection. There is no intersection. So one can use either the methodology in the black or the methodology that I show using the magenta color. So in this course, I will be using the magenta color, because that makes, schematics less clunky, right? But as long as you understand what I am trying to convey, it should be fine, because sometimes you'll see that it's not possible to sketch schematics without crossing over, and you might see something like this. You will see something like this, but this doesn't interpret that there is a crossover. This will interpret that there is no crossover. If there is a no junction dot, there is no crossover. This is called a junction dot. Right? So very trivial stuff, but things that can lead to misinterpretation of a question, right? So it's better to get these things clear. Okay. So now let's move to today's main point of discussion. So let's take last time we were trying to figure out the generalized framework using multi loops. What I'll do today is develop a framework using a single loop and then extend it to a more generalized multi loop network. So let's say this is again an applied voltage VA. You have a voltage drop of, let's say here, V1. You have a voltage drop of V2. This current is naturally I1, and this current will also be I1 because they are in the same loop. So next step is I say that I apply I change the voltage VA by small amount, whatever that small might be. So let's say I call this VA plus incremental VA. By incremental, I am representing as small v, small a. So this voltage naturally will also change, and I denote it as V1 plus small v1. Here, 1 doesn't have a subscript, shorthand, so can't do anything. So this is I1 plus I1. So this is V2 plus V2, and this also I1 plus I. Okay. So now here was the confusion, which I'll try to address in a different way today. So let's take this guy, and I redraw the same schematic using a bigger area. So tell me what's going to happen if I, let's say, break this here and insert a voltage source of value 0. Nothing going to change, right? You all agree? Okay. So now 0 can be added in different ways. So what I'll do is I will add. So given that I know in this loop, I know that VA minus V1 minus V2 is equal to 0. I will add a 0 in this format. Okay. So what I'll do is I will add a VA here. I'll add a V1 here. Please note the directions in which the batteries are being applied. So essentially, I apply 0 volt. We all agree? So no change in current voltage anywhere. Okay, great. So next step is, I'm sure many of you are seeing what's coming. So this, I'll take this V1 out of here and add it in series with this guy. Okay, so let's do that. Okay, and next I'll take the V2 out and add it in series with the other element. Fine. No change anywhere. Okay. So this is as far as using the voltage sources, using KVL essentially, right? Using KVL to manipulate the DC voltage sources. Okay. So next thing is, because the whole purpose of this exercise is to subtract the quiescent from the total to get only an incremental network, right? So an incremental, when you are doing incremental network, we are dealing with incremental voltages and also incremental currents. So by doing whatever we did now, we can probably subtract the total voltages and get the incremental voltage, but we will not get the incremental current. In order to get the incremental current, we have to subtract the current also. And KCL will help us in doing that. Okay. So again, just like KCL, just like KVL deals with voltages, KCL deals with current, and we'll use the same principle. We'll add 0 current to a node. Okay, and again, 0 current to a node can be done in infinite, can be made in, can be added in infinite number of ways. So what I'll choose is one way where I'll say a current of, let's say, I1 comes out of this node in this way and goes here. A current of I1 comes out of this way and goes here. And similarly, a current of I1 does. So do you see, if you take any node, if you take, for example, this node, no extra current is coming in, right? I am taking out I1, but I am putting the same current back. Similarly, it goes for all the nodes. Fine? Okay. So essentially what I am doing, what is the whole purpose of doing this thing? Now, what I'll do, I'll club these guys together. Okay. So and let's focus on only one of the elements. Let's focus on this section. Okay. So we all agree that the voltages across the nonlinear element hasn't changed, or the current through the nonlinear element hasn't changed. But now if I assume my new element is the box that I have, or the circle, or the elements that I have encircled, right? So if I assume that this is my new element, so this was V1 plus V1. This is V1, this is I1. This current was I1 plus. Well, let's assume this is my new element, not the nonlinear element only. This total stuff is my new element, and I'm only looking into these terminals. Okay. So what will I observe? What will I observe from outside? It will seem to me that the stuff inside this box, right? Stuff inside this box, or rather, what will I observe? What current will I see that is going into this box? Small I1. And what will be the voltage that I will see across this? Small V1. Right? So essentially, if I look from outside, if I don't know what's inside the box, it would seem to me that I have an element, some other element inside. The voltage across which is small v1, and the current through which is, direction is wrong, the current through which is small r. Do you agree? Fine. There seems to be some hesitancy. So what is the hesitancy? So think that you don't know what's inside the box, right? You are looking from the terminal. You don't know what's inside the box. Then the only thing that you can observe is the current that is going to the box and the voltage across the ports or the terminals of the box. That's all I am doing. If I observe that, what will I see? It seems like a new element which is only having terminal voltages which are incremental, right? And not the total, and also a current which is an incremental current. Agree or don't agree? Okay. Okay, fine. So if this is the case, now I hope that it will probably be easy to convince you that if there is a multi-loop system, this is a single loop example that we did. So let's say we have a multi-loop stuff. Maybe something like this. All of these are nonlinear elements. So what do we need to do? We need to satisfy KVL and KVL through each of the loops and KCL at each of the nodes while adding zero current. That's all we need to do, right? So essentially, if I find out any element, let's say kth element, and I see that the voltage across it is Vk plus small vk, and the current through it is Ik plus small ik, right? So any arbitrary element. So all I have to do is to replace this guy, or not replace, simply maybe add another contraption, which will be of this format. And I go and do this to all elements in the loop, all elements in the network, right? So if we do this, what the new network that I will be left with will be a network in which I have only the incremental quantities, right? Or no? I mean, for example, in this case, this contraption will be replaced with only small VA, right? The incremental quantity, incremental applied voltage will be the small VA. The current through each of these contraptions will be small I1, right? Similarly, in this case also, if we satisfy KVL, since we are satisfying KVL at each loop, and since we are satisfying KCL at each loop, right, by adding zero voltages and zero currents, so the similar principles will hold, and we will be left with a network where there are no original voltage, I mean DC voltage source or DC current or operating voltage source or current sources. We will only be left with the incremental ones. Agreed? Now note that till now we have not made any approximations. No small signal approximations anywhere. We are only saying that if I apply an increment here, some increment will happen there. Okay. So if that is the case, if I take any network, now I don't have to show all elements in the network. I take any network and say that I have an incremental element. I mean, this is the bigger part of a network. Something is connected across its ports. Questions? Okay. Something is connected across its ports. All we are saying is if there is a voltage, incremental voltage, let me go back to the delta notation to make this point. If there is an incremental voltage delta Vk, sorry, this is Ik, and incremental voltage, messing up the notations. So this is equivalent to small Vk, this is equivalent to small Ik as per the notations. So how do I how do I make use of this to make my life simple? That is something that we have done earlier. And what was it? We will say that if the current voltage relationship of this nonlinear element, let's say Ik, I know to be some nonlinear element f of some nonlinear voltage across it, right? Some nonlinear function of the voltage across it, then I can say that delta Ik is equal to some factor times delta Vk, right? And this factor is equal to 1 over del I del V around the operating point of Vk Ik. Here we are invoking the small signal approximation. So this is while neglecting higher order derivatives. So here we are invoking the small signal approximation, right? So this is using small signal approximation. Okay, make sense? So why am I going through all of this? Because what generally tends to happen is, since we develop this framework using, using set of equations, right? We write out the quiescent, we write out the incremental, and we subtract. What in general, what we tend to do, even when we give you some circuits, there is a tendency to write out the full equations of all of them and then subtract. That is okay if you have one or two elements, but it becomes tedious if you have multiple elements in the loop. Then you have to write equations for each of them, and you will, even for a two-loop system, you will end up with 2 pages of equations, which is not only time consuming, that is, you might make some approximation mistake here and there, and that can lead to some unnecessary penalty. So yes. Can you repeat? Okay, yeah, correct. Yeah. Thank you. So this is supposed to be conductance, right? Yes, thank you. So this will be del I del V for IK VK. Right? Yeah, thank you for pointing it out. So again, okay. So this, since we are at it, so this we say is the incremental conductance. This is the incremental conductance. So if this incremental conductance, if this derivative is fully real, right? So what we can simply do is, to finish the thought, we can replace this box now with a resistor or a conductor, a resistor of value 1 over del I del V, and which has a voltage of Vk and a current of small ik to it. Okay. Thank you. Thanks for pointing it out. Okay, so yeah. So what I was trying to get at here is that when you find a network with a single nonlinear element or multiple nonlinear element, don't go about writing both the equations and then subtract. All you can simply do is to find out the operating point, right? So step 1 will be finding out the operating point. Step 2 is finding out the derivative around the operating point. And step 3 is replacing that nonlinear element with whatever that 1 over derivative is, right? And then go ahead and solve that perfectly linear network, right? So that's essentially the 3-step process that we'll follow throughout this course. Any questions? Okay. So since we are at it, it is instructive to characterize all the elements that we already know and see what the small signal equivalents are. Okay. So we already saw the small signal equivalent of a diode, right? The small signal equivalent of a diode was what? Yeah, please speak out. A resistor, right? Great. So it's a resistor of value VD over ID, right? So this is a resistor of value VD over ID. So what about the small signal equivalent of an actual linear resistor? It's a resistor, right? And how do we get that? It's basically IV characteristics of a resistor is a straight line with a constant slope right? Slope is 1 over r. So you do a derivative, you get the same thing. So this becomes r. Great. So what about let's say a voltage source? What is a small signal equivalent of a voltage source? Pardon? You don't have to remember. You can just figure out with the logic that we just did. So what are you replacing this with? What are you replacing any element with? Can't hear. Can't hear. Can you speak up? Correct, right? So what will that equivalent be in this case? 0, right? So because IV characteristics of this will be, so this is IV. So IV characteristics is essentially this. So del I del V is infinite, right? So which essentially means that 1 over that is 0. So this becomes a short circuit, right? So a constant DC voltage source gets replaced with a short. Okay. So the next thing will be simple then. So let's say we have a constant current source. So it will naturally get replaced with an open circuit, right? So this is an open, short. Okay. So what about, let's say, I say a capacitor. You can speak up, anyone. And you can speak up, I mean, just share what you are thinking. It need not be the right answer or need not be the answer also. Yes, effectively it's an impedance, that's correct. So, right, in DC it is 0. So, the other way around, DC it is open circuit. And in higher frequency it will be 1 over something, right, J. But when we say 1 over J omega C, we are not in the time domain, right? That's a phasor notation. Right? So when you replace a capacitor, the impedance of a capacitor with 1 over J omega C, what does omega imply? It's a frequency which has been applied by some source in the network. Omega is a frequency, but what frequency? It's not any arbitrary frequency. It's a frequency of some source that has been applied to the network, or the network is being excited with certain frequency. If the network is getting excited with a frequency of 1 hertz, then the capacitor will give its impedance of 1 over 1 hertz times 2 pi times C. If it's like 1 gigahertz, it will be 1 over 10.9 times 2 pi times C and so on. So it's a change in frequency. It's a change in impedance with respect to frequency. That we understand. But everything is in phasor domain. Whenever you get into omega, you are talking about a phasor domain, right? So using phasor domain, it's easy to see. Right? Using phasor domain, it is if we extend all of these arguments in the phasor domain also, what we can simply say is that a capacitor gives us, if I apply a voltage of V, the current will be J omega C times V. Right? So slope seems to be that 1 over, slope seems to be J omega C. So I replace a capacitor with a capacitor, which in fact it is correct, but in the phasor domain. But if I have to, since we are doing everything in time domain, if I have to draw an analogy with time domain, how should I go about doing it? Because things like a capacitor is I C dV dt. There's a derivative there, right? So, but why do you say it should be a nonlinear resistor? Right. Correct. So what he is essentially pointing out is it seems like there is a derivative there, and if I go into, if I then integrate it, then it can become nonlinear, right? If I integrate a linear function, it can become a nonlinear, the expression can become nonlinear, which is in fact correct, but the reason this is not valid here is because what is the fundamental nature of a capacitor? The fundamental nature of a capacitor is that the charge is proportional to the voltage. The linearity is in the charge domain, right? So since the capacitor is, whenever you say I have a capacitor, you essentially means that of value C, essentially what you imply is that if I apply 1 volt, I will get a charge of C times 1 volt farad, or rather coulomb, right? So that's what the relationship is. So as long as this relationship is linear, the capacitor is linear. Okay, so essentially we replace a capacitor in the incremental sense with another capacitor of value del Q del V. But you don't have to worry about del Q del V in this course. All the capacitors that we'll be using will be linear. So essentially you can replace all capacitors with a capacitor of same value. Okay. Yes. Okay. So the reason we went into, so what is so holy about this del I del V thing? We started off with I and V. Since we are trying to relate incremental voltages with incremental currents, we ended up with del I del V, right? But when you are dealing with a capacitor, fundamentally, when we study capacitor, we study the relationship between the voltage across its terminal and the charge that is held, right? The current is essentially a derivative of that because we have to sometimes relate everything in a loop format. But when we do a derivative and relate in a loop format, essentially what we are saying is that in all those analyses that we do, we go into the phasor domain. Because we do a derivative, we get into this j omega comes out, right? When we apply a sinusoid of e power j omega t, right? And then you take the derivative out, then it becomes j omega comes out, then you put, I'm sure you have done this. You have done this in an LTI. What is the ideal function of an LTI system? Exponential, right? So, and if e to the power st essentially is the ideal function of a nonlinear or linear system, LTI system. And why do we say it's an ideal function? Is because if we apply the input, the output will be some scalar times that function, right? In case of a capacitor, that scalar becomes j omega. If we apply a voltage of e to the power j omega t across the terminals of the capacitor, the current will be ddt of e to the power j omega t, which is j omega times e power j omega t, which means j omega times the voltage that you have applied, j omega c times the voltage that you have applied. The j omega c, essentially we call it as the impedance, right? So that there comes the linear relationship, right? So in the phasor domain, that's why if you do this, if you do the analysis in the phasor domain, it actually comes out the capacitor gets replaced with an impedance of the same value, right? But when you are doing time domain, in the time domain, essentially the relationship of the capacitor comes from the U equal to CV characteristics. So if the capacitor is nonlinear, which essentially will mean that this characteristic itself is nonlinear. You can have capacitor whose capacitance changes as you change the machine, which in fact is a very practical scenario. I mean, for those who will be taking 311 or other device type of courses, you will see that in microelectronics, in VLSI, almost all capacitors are nonlinear. So in those cases, what you tend to do is to say that since we cannot do any analysis using Q equal to CV then, because the moment I change V, Q also changes, I mean C also changes, then we have to define an operating region of the capacitor, and then that operating region will have some incremental capacitance. That capacitance is del Q. Okay. So, I mean, to cut a long story short, you find any element which is nonlinear, go back to its original roots and find out what was the original root equation. If that equation is linear and still holds, replace that element with itself. If it doesn't hold, replace it with the derivative of whatever the original case was. Okay. Okay, so fortunately in this course, no nonlinear capacitance. So it's all C. So since we did capacitance, we can also do inductance. L gets replaced with an L. Fundamentally, as far as the mathematics is concerned, there is no difference between the between an inductor and capacitor, just that in one case you have a voltage, which is a dependent variable. In that case, you have a current that is a dependent variable. Okay, fine. So now, since we don't have much time, let me leave you with one critical concept which we will be using throughout the course. Its time will come in another, probably tomorrow, but let me try to give you a sneak peek. So we said that the incremental nature of a voltage source in the incremental model is a short circuit. Correct? So another way of looking at it is, if I push an incremental current, right? If I push an incremental current into the voltage source, it will not cause any change in the voltage across its terminals. Right? Very rudimentary basic definition. What does it essentially mean? If I say that any incremental current is not causing any incremental change in voltage, which means the incremental resistance is 0. I push in current, no voltage change, which means naturally the resistance is 0. In this case, the voltage is there, but the increment is 0. Right? Since the increment is 0, the incremental resistance of a voltage source is 0. Right? That's the intuition behind it. So now, can you tell me, is it possible in any under any circumstance to approximate a capacitor as a voltage source? The symbols also look similar. So is it possible to replace a capacitor with a voltage source under any conceivable circumstance that you can think of? Pardon? Very large tau. Okay. Very large time. Okay. Let me probe you a bit further. So why do you say very large tau? But it will eventually discharge, right? So I appreciate the thought process. You are on the right track. So the point that she was making was a capacitor with a very large time constant, right, can probably be replaced with a voltage. So I presume, because, I mean, not presume, she said that because it will discharge very slowly, which is correct. But my counter was, it will eventually discharge, right? This voltage source will never discharge, but the capacitor will eventually discharge, right? If I put something across it. Saying something? In an AC circuit. Why do you say AC? You are correct. You're correct. I'm going to probe you on that a bit more. Yes, there was something here. No. Okay. So so before I go into this high frequency stuff, so let me take from whatever she pointed out. So let's say I have a capacitor, something like this, and I have a voltage source. So in this case, I applied a voltage source. If the capacitor was initially 0 volt, after infinite time, it will get charged with the value of the voltage source, whatever voltage was being applied, right? So it seems that the voltage across the capacitor is changing. So which means that it should not be a voltage source, right? Had it been a voltage source, the voltage across the capacitor wouldn't have changed. Okay. So now, what will be the profile with which the capacitor voltage will change? This is the, let's say, VC with respect to time. So it will do something, assuming it's initially uncharged, or let's assume it is initially charged, right? Let's assume it is initially charged with some voltage. And let's say this was 1 volt. And you apply 2 volt here. So eventually it will go from this 1 volt to 2 volt using that famous curve, right? We all know. So if I use another capacitor of higher value, right, how will this charging look like? It will be shallower. Correct? And if I choose a capacitor of almost, whatever the maximum value that you can think of, it probably will do something like this. You have to go all the way to Kalyanpur to see where anything has changed, right? So now but eventually it will get charged. But now if I restrict my time of observation, if I simply say that I am only going to observe till here, then it seems like the capacitor has held on to this original charge. Correct? So that's where she is correct, right? So if I limit my duration of observation, then the capacitor can behave as a voltage. Correct? So now let's assume that, so limiting time of observation can be okay in certain circumstances, may not be okay in other circumstances. But let's assume that this 2 volt battery is not a 2 volt battery. This probably goes like this. It goes from, I don't know, maybe 1 volt to 2 volt. It goes like this. Right? And that is somewhere here. So do you think qualitatively, in the time scales that I have shown, the capacitor will hold on to the original voltage or will be changing its original voltage? Approximately. Using the very large capacitor. Maybe the question is not clear. Maybe I'll ask you in a different way. Okay, let me give you another analogy, right? Forget about this one, right? So let me give another analogy. So let's say I have an ideal current source, which is dumping voltage onto a capacitor. Okay. So the current source, let's say, starts from t equal to 0, and it's a sinusoid. Okay. So what do you think the voltage across the capacitor will look like? Let's start from t equal to 0. Right? Let's start from t equal to 0. What should I do? So voltage is 1 over c integral of I dt, right? So I will do a graphical integral. So what should it look like? It should integrate and it should increase till here. Let me use a different time scale or different. Let's assume the capacitor is not very big, it's very small, which means it will go something like this, go all the way here, then it will increase and it will do something like this. Correct? So what do you think this is a twice the amplitude. What do you think this twice the amplitude is implying? It's the voltage across the capacitor, right? The change of the voltage across the capacitor as the time changes. Now, if I increase the capacitor value, what's going to happen? So it's 1 over c times this, right? So this guy will not be able to change as much. And if I keep on increasing, if I go to an infinite value of capacitor, it will become a flat line. So I'm applying a volt current, incremental current, changing current, but there is no change in the voltage across the capacitor, which means it's a short circuit. It's an incrementally short circuit at this frequency. But if I change the frequency, for the same value of capacitor, if I say that my frequency is something like very small, so this capacitor is, for the very large value of capacitor also, it's getting sufficiently long time to charge up. Right? So what's going to happen? This guy was, even though this is the slope is very shallow, but it's getting a long time to charge up. It's like even though you have a large time constant circuit, but you have infinite time to charge, it will eventually charge, right? For the same frequency, if for the same capacitor, if we change the frequency, it might not look like a short circuit, right? So because this amplitude, how much is it going up, is the critical thing to observe. Okay, so that's why the change comes in. The change becomes important. That's why at AC, a capacitor can behave, a large enough capacitor can behave like a short circuit, but not necessarily at DC. Because at DC, everything will be open, because eventually the capacitor will change its charge, change its voltage. Okay. Okay. Thank you. We'll meet tomorrow.